This video is about the design and development of this 6 degrees of freedom robotic arm. It can be controlled using an Xbox game controller, features inverse and forward kinematics via a custom Unity frontend, and the entire thing is open source. Let's get started by looking at how the first joint works in 3D. Starting with joint 1, we have a NEMA 17 with a small pulley of 16 teeth using a 10mm GT2 timing belt driving a larger pulley of 130 teeth, which moves this 3D printed carrier plate, which is supported by 2 taper roller bearings. On to joint number 2, where the driver for this axis is this 3D printed cycloidal drive, which gives a gear reduction of 34:1 and is driven by a larger NEMA 23 motor. This power is transmitted through a central shaft onto a 3D printed carrier plate, and this assembly is also supported by 2 taper roller bearings. This limit switch on the side is used for homing joint number 3. Joint number 3 uses a pulley and belt mechanism like joint number 1. The large pulley there has 96 teeth and the small pulley has 16. There is a limit switch on the base for homing the next joint, joint number 4. The bearing assembly is made up of 2 deep groove ball bearings to account for the radial load on the joint and 2 thrust bearings to account for the axial load. Rotational motion goes through the pulley via a central shaft onto a driver plate, which moves the next joint. Joint number 4 is very similar to joint number 2, only this time a smaller cycloidal drive is used, this one giving a gear reduction of 21:1 and also using a smaller NEMA 17 motor rather than a NEMA 23 as was on joint number 2. The power is once again transmitted through a shaft onto a carrier plate. There is a handle on that carrier shaft which engages a limit switch in order for the connecting joint to be homed. The goal for joint number 5 and 6 was to keep the weight as close to the middle of the robot as possible. This was done by keeping the 2 motors that drive the joints further back and have their motion transferred through a couple of shafts driving 2 smaller pulleys. The pulleys would have timing belts that wrap around these idler wheels that ultimately drive these larger pulleys, which are responsible for driving joint number 5 and 6 respectively. Joint number 5 is directly driven via the pulley, and joint number 6 is driven by this bevel assembly, which allows the rotational motion to be transferred by 90 degrees. The 2 limit switches added to the housing allows these 2 joints to be homed. Fabrication of the first joint is done on 9mm MDF. It took a couple of passes on the laser cutter to cut all the way through. And then it was time to assemble the first joint. That's the taper roller bearing being attached to the top of the housing. The pulley gets screwed in next, adding the timing belt onto the motor. The slots there allow the tension on the belt to be adjusted. And the same for the bottom part of the housing. The second taper roller bearing gets attached with the little connecting plate. And then it's a case of putting the rest of the housing together and checking that the joint is functioning as expected. Joint number 2 now starts with adding the taper roller bearings onto the end of the housing. The joint then gets bolted down onto joint number 1. Those are 5mm bolts. With the housing set, it's time to assemble the main driver of this joint, the cycloidal drive. First the pins go on, and there's quite a few of them, so that took a while. And then attaching the housing to the motor, which was quite tricky because there's no threads for those bolts, so holding down the nuts on the other side and then doing my best to get those as tight as possible. The eccentric shaft and the first cycloidal disc gets attached with the bearing joining the two up, and then the second disc gets attached, which is then held in place by a set screw. Finally, I just tested to make sure that there was nothing catastrophic that had gone wrong and it was working. Adding the output shaft next, and the output pins are just 3 8mm bearings on a bolt that then gets screwed in to that 3D printing housing. The top cap gets added on, and finally I can attach the output shaft. The field density was really quite important for this output shaft, considering the weight it had to drive. I printed some earlier with 25% density and it pretty much snapped off during testing. So these ones were done with 50%. Could still probably do with being a bit higher, but I found that value was a good compromise between strength and sensible printing times. The output plate is then attached via a taper bearing, screwed in, and that is finally attached to the output shaft via 4 bolts. And a final check just to make sure the joint is working as expected before moving on to joint number 3. Joint number 3 starts with the motor being attached. The slots there allow the tension on the belt to be adjusted, and then the bearing assembly is added. The pulley gets attached next. This is driven by the motor on the other side. And finally, that subassembly is attached to the frame via a circular pattern of 5mm bolts. Joint number 4 now, and there's the output shaft being attached to the front plate of the housing, and then the cycloidal drive being bolted in. And then I can assemble the joint on the robot, which made those mounting blocks very, very useful, as it allowed part of the frame to be attached and assembled, and then the other part to be joined later. Here's the frame for joint number 5 and 6. Some of this was held on using those mount blocks, and some of this was glued on to save some weight. And in the spirit of saving some time, here is the fully assembled joint. Joint number 5 being driven directly through that pulley, and joint number 6 using the bevel assembly to turn the end joint. And finally, it was a case of bolting that subassembly to the final frame, and that completed the 6 joints for this robot. But it was unlikely to do anything unless there was some electronics, and that was the next phase for this project. The main driver board here is a GTEC or a GTEC 2560. That's essentially a 3D printing board where an Arduino Mega and a RAMPS configuration are merged into a single PCB. The caveat with using this board is that it only supports 5 stepper drivers, which is the case for most 3D printing boards, to be fair. So I had to add an extension module for the 6th motor, which were readily available on AliExpress or Amazon, and the module worked pretty well. I just had to custom configure them in the firmware and I was good to go. Speaking of firmware, this project ran on the 6-axis version of GRBL, and this worked fantastically well. I found the axis extremely easy to configure if you are already familiar with the regular 3-axis GRBL. So thank you very much FRA 589 for this port. I added larger TB6 drivers for the first 3 joints as they would be driving the most weight, and smaller A4988 drivers for the last 3 joints as there wouldn't be as much force on these joints, and I could finally give it a test. This was the main stress test of the robot, where the joint is fully extended and making sure that it doesn't collapse on itself. I kept my hand there underneath just in case that's what it decided to do, and then I managed to move it around the limits of the joint just to make sure the joint's held. And this is the machine painted with blue and yellow. Here's where the idea of theming this came really. It wasn't originally planned that way. The tone of blue and the tone of yellow kind of just lent itself so well to Fallout that I just lent into it and went ahead and laser cut the logos. Of course, there's no official affiliation here between that game, but I did think it gave the project a bit of fun. And also Fallout is just awesome. Final test done with a game controller first. That's using the universal G-code senders feature of jogging with a gamepad, which worked pretty well and allowed me just to test the initial joints were working as expected, because there had been some time between me actually finishing the unpainted version and me testing this final version, so I wasn't exactly sure where the project was at in between. Inverse kinematics was next, and I wrote this Unity program to help facilitate this. The actual calculations are done using a library by Eric Voll, which was available on GitHub, that does all the nitty-gritty math calculations, and my code was a bridge for using those calculations to produce some G-code that can run on the physical robot. So thank you to Eric Voll for making that library available, and it worked very, very well. This is me moving the target, and as I move the target I press capture pose on my software, and that essentially creates a keyframe for this robot. Then move it to a different position, hit capture pose one more time, and I carry on doing this until I've got the movement that I want. This would have been, so I'm moving the target there and you can see the robot following, and then I would capture that pose one more time. I can do the fine adjustment by using the inspector values directly. One more final pose, and then I do write to file, which saves the output, and then I can play back what I expect the motion to look like. So that's what I'm aiming for with the kinematic movements that I just captured. The G-code is written to a file when write file has been pressed, and I can send that G-code file to UGS. I can send that to Universal G-code sender and have that run on the machine. Here's a simple square shape done using inverse kinematics. And finally, a test of all the axes moving at the same time. And with that, I'd like to thank you all very much for watching, and maybe I'll see you next time.